So, very good morning students. Welcome to the Shankar Medico Academy. This is one of the premier institute for a NEET training program for NEET aspiring students, medical aspiring students. And today we are going to discuss one of the important topic in chemistry, that is chapters called chemical bonding and molecular structure. Let us go to the chapters here. And in this chemical bonding and molecular structure, there are many subtopics. Let us say, for example, chemical, coordination, bond, ionic bond, and covalent bond, and in addition, hybridization, molecular symmetry, many things we are going to discuss. And of course, within the time limit, this is one of the important topic, most widely misunderstood concept in chemical bonding, that is, we can call it as isostructural species. Let us see very deeply what is called isostructural species. Before going to see what is isostructural species, we have to know what is isoelectronic species and what is isospheres. These two species already we have might be known from the previous chapter called structure of atoms. Generally, iso means the same. This is what we have to know. Now, we can easily understand that isoelectronic species. Isoelectronic species means the species having same electron, the same number of electrons. This very simply we can call it as whatever the species, whether it is cation or anion or neutral, that species should have the same number of electrons, that is comes under isoelectronic species. For example, F minus, N3 minus, Mg2 plus, these are all some examples. It has a 10 electron system, fluorine atomic number 9, and it has one negative charge, so that 9 plus 1, 10, and nitrogen 7, 7 plus 3, 10, and magnesium 12. That is a cation. We got to subtract the corresponding number of charge of positive charge, so that 12 minus 2, 10. So this species called a isoelectronic species. And simply come to our isostructural species, isospheres. These isospheres means what we should understand, that the species have the set of species have same number of electron and same number of atom. So whatever you have the isoelectronic species, and those kind of isoelectronic species must contain same number of atom. That is, atomicity should be same for all the particular set. Atomicity, number of atoms present in the molecule or ions called atomicity. So that if both meeting this criteria, both same number of electron and atomicity, then it should be the isospheres. So let us go for some of the examples. We can go for you can see here, isoelectronic species, the set of molecules or ions and or atoms, anything, whatever, having same number of electrons are called isoelectronic species. See, for example, N3 minus, O2 minus, Mg2 plus, these are all one kind of sets, 10 electrons. And if we come to the molecules, nitrogen is a molecule, carbon monoxide is a molecule, both having number of electron is nitrogen 14, 14 plus 14, 28. And if you come here, CO, carbon number, 14, not 7 electron, right? This is a 7 plus 7, nitrogen 14 electrons. Whereas carbon monoxide 6 plus 8 equal to 14 electrons. So this also one set, and this another set, and you can come here nitrate and carbonate. So in this case, how do you count the number of electrons? For in this kind of species, maybe sometimes you can just ignore the, I mean, you can eliminate the number of common atom in both molecules, so that it has O3 minus and this the O3 2 minus. Just 3 oxygen atom is common for both. In this case, you don't need to count number of electrons all the way, just take n minus, and here is C2 minus. N minus 8 electrons, whereas C2 minus also 8 electron. So that this molecule also same number of electrons, so that this molecule comes under isoelectronic species. Okay, this is very simple definition, and we can go for here isospheres. Isospheres again is another set, a set of molecules or ions have the same number of electron as well as same number of atoms. This is a simplest definition, so anyone can easily understand that. How do you see, how do you identify a set of isospheres? Let us say, for example, carbon dioxide and nitrous oxide. This is the azide ion, and this one more is, this is alene. This is called alene. Alene having carbon double bond on both sides and CH to CH2. In carbon dioxide, terminal 2 oxygen was removed by CH2. So this is a way it's actually working. Maybe we can check whether CO2 molecules comes under this category. And you can see CO2 carbon atomic number 6, oxygen atomic number 8, 8 plus 8, 16, 16 plus 6, 22 electron totally. And nitrogen, nitrogen 7, 7 into 2, 14, 14 plus 8, 22 electrons. And N3 minus also 3 into 7, 7 atomic number for nitrogen, so that 1 minus also there, so that 21 plus 1, 22 electrons. So, and at the same times, you can see the number of atomicity is 3 here, here also 3, here also N3 minus 3. So, this set of species except alene. So, carbon dioxide, nitrous oxide, azide ion both having same number of electron as well as same number of atoms. This is called isospheres. And when we come here, let us check the here. I mean, this is a alene, 3 carbon, 3 into 6, 3 into 6, 18. 18 plus 4, 22. Yeah. Let us check this carbon dioxide. Carbon dioxide, 16 plus 6, 22. So, you can look at all the 1, 2, 3, 4, 5 species. All the 5 species having number of electrons is same, 22 electrons. But this atomicity, alene having atomicity is how much? 3 carbon, 4 hydrogen, 7 atomicity. Whereas this is a 3 atomicity. Number of atoms is 7. So that definitely CO2 already, of course, here is already explained. Okay. So then this is a 1 ruled out. This is not the isospheres within the set. In fact, it may be, we can call it all together, is comes under isoelectronic species. And here, this is a point you can easily note it down. Isospheres, all isospheres are isoelectronic species, but all isoelectronic species are not isospheres. This is a meaning, we can easily understand that. And in fact, you can see that another 2 species. NO2 plus, nitrogen dioxide, that is NO2 plus, one of the aromatic electrophile reaction, nitration, it is one of the electrophile, famous electrophile for nitration reaction. Cyanides, both having 22 electron system. Of course, this also atomicity 3. So, nitrogen dioxide, NO2 plus electrophile, cyanides and CO2, N2O, N3 minus. These are all not only isoelectronic species, at the same time it is all isospheres except alene. Okay. I hope isospheres everybody well understood. Next we will go for next slide. And now you can see here methane, ammonia, water, HF. These are all pure molecules. We can easily able to handle, these are all isolable. So everything having a 10 electron system. But number of atom is, each set is different. This is atomicity is 5, methane. This is 4, this 3, this 2. So these sets are isoelectronic species, but not isospheres, because number of atoms is different. And come to this point, next one, sulfate, PO4, phosphate, and perchlorate ion. And these 3 species having 4 oxygen atom is a common, just a common atom, just remove it and you can take it as S2 minus and P3 minus and Cl minus. Sulfur atomic number 16, 16 plus 2, 18, phosphorus 15 and chlorine 17, so that it is actually 18 electron system. So these are all isostructural species. Okay. Let us see within the introduction of isostructural species, isospheres as well as isoelectronic species. Let us go for isostructural species next. Now come here. Now what we can understand that what is actually isostructural species. Before going to explore all those possibilities, we should know actual what is meaning of isostructural species. The molecules or ions or any species having same hybridization, same geometry, shape of the molecule and hybridization. These should be same. This is one we need to understand the first. Geometry or both are same only. It should be hybridization, intermixing of orbitals called hybridization. And for hybridization of any molecules, it is easy to calculate by knowing this general format, and the hybridization is equal to 1 by 2 V plus M plus A minus C. V means it's a valence electron, number of valence electron of the central atom, number of valence electron only. And M stands for number of monovalent atom. Whatever the valency is number 1, it is directly attached to the central atom, that is corresponding numbers. And A number of anions and a number of cation. Generally number of anion should be plus, because it is contributing 2 electron to make one bond. That's why it should be plus. Whether it's a cation means there is a shortage of electron. That's why you have to remove this, subtract the number of positive charges, that is the number of cation or positive charges. So now it is easy to execute this hybridization formula by some set of molecules, from using some set of molecules. Let us say boron trifluoride. Boron trifluoride BF3, NO3 minus nitrate, that is carbonate. And for BF3, boron is a central atom. It has 3 electron in the valence shell, and it is also having 3 monovalent atom attached, that is fluorine. So 3 plus 3, it is a neutral molecule. There is no positive charge, there is no negative charge. So that 3 plus 3, 6 by 2, 3. This is 3 stands for 1 s orbital and 2 p orbitals. So that 1 plus 2, 3. So this should be sp2. And come here is NO3 minus. NO3 minus 1 by 2, that is nitrogen is a central atom. It has a 5 electron in the outermost shell, and it is also having one charge, one negative charge, that is a number of anion is 1. So 5 plus 1, 6 and 2, of course this is also sp2. And carbonate. Carbon is a 14th group. It has 4 electrons in the outermost shell, and it does not have any monovalent atom. and it has a 2 negative charge, so that 4 plus 2 divided by 2, that is a 3, it is also sp2. So all these molecules having same hybridization, and we have to look at this one, even though it is a same hybridization, but ensure that all the central atom should be, in this case it does not have any lone pair of electron, only bond pair of electron. Ensure that all the nitrogen, many cases nitrogen has lone pair electron, but it is supposed to do not have lone pair electron. This also ensures that before going to drop a shape of the molecules, so that remember all the carbon, nitrogen, boron do not have no lone pair of electron. This one conclusion you should get it. And now, of course, before here I can easily say that these are all what is called a planar molecules. Planar, that is a B, F, F, like this you can put it like this. Of course, NO3 minus also you can put it as NO3 minus, this is a simply, okay, this is actual structure, I do not want to go for much explanation. So 1 plus 1 positive, 1 negative charge gets neutralized, remaining 1 electron is 1 negative charge is excess, and of course it has 3 sigma bond, definitely it is a sp2, and planar molecule 120 bond angle. In fact, what is another one, CO3 2 minus also, you have the one double bond and the carbon valence always 4, and just minus, it has 3 sigma bond, and this is also a planar molecules. So that let us go for another one, and isoelectron species, another example. This is a ammonium, this is a perchlorate ion, this is sulfate ion, and you can see here ammonium cation, there is a ammonium ion, it is a nitrogen, the central atom, and 4 monovalent attached, and it is a positive charge, 1 positive charge, so that minus 1, it is a totally 4, that is a sp3 hybridization tetrahedral. And chlorates. So perchlorate 1 by 2 is a format, and chlorine has a 17th group and 7 electron in the outermost shell, and it also having only 1 negative charge, all the oxygen having, it is not a monovalent atom here, and it is also obeying sp3 here, and SO4 2 minus. Sulfur being the 16th group, it has 6 electrons in the outermost shell, and it has 2 negative charge, and it is also having 4 sp3 hybridization. So if you look at these molecules, and while writing the structure of the molecule, ensure that it has to match the balance of the central atom. It is very most important, and nitrogen 4 bond we made because of the NH3 plus 1 H plus and a cation, and of course this is a positive charge, and it has a 4 sigma bond. 4 sigma bond means that is always tetrahedral. And of course chlorates, perchlorate chlorine, 7 valence electron, 7 bond you can see here, and 4 oxygen. Out of 4 oxygen, 3 oxygen having a triple bond, double bond, only 1 is this one. And look at this number of double bond, number of sigma bond, 1, 2, 3, 4. So this also a tetrahedral, and here also sulfate, 16th group, 6 bond it must have, and it also having a 6 bond, out of 6 bond 4 sigma bond. So this also tetrahedral. So definitely these molecules, what we can say that all of them isostructural species. Sometimes there are some molecules having not only isostructural species, it also match with the isoelectronic species, but in this case it does not work out. Maybe chlorine, this is Cl minus, this is S2 minus, these are all out except ammonia. chlorate, sulfate, these are all. And what is another one? Is SO4 2 minus. Isoelectronic, isosphere, as well as isostructural. So, very interesting to correlate isoelectronic species, isospheres as well as isostructural species, but these two is matching for all these three category, right. So, now let us go for here. Some molecules are the example of isoelectronic species and isostructural species. Of course, once isoelectronic, and we got to see the number of atoms. If it is atoms are equal, it also comes under isospheres. SO3 2 minus, PO3 3 minus, ClO3 minus. This is a sulfite, this phosphite, this is a chlorate, not chlorite, chlorate, because perchlorate ClO4 minus. And this is a SO3 2 minus, sp3 hybridization, and you can see that sulfur 6A and 2 minus sp3, and PO3 3 minus, this also sp3, and this also sp3. According to the hybridization formula, everything sp3, but ensure that it is not a tetrahedral structure. Don't think that always sp3 comes as a tetrahedral species. We got to look at the central atom whether it has a lone pair electron or not. If it has lone pair electron, it should be pyramidal. You can see here sulfur totally 6 electrons in the outermost shell, 1, 2, 3, 4, 5, 6, and 2 minus okay. And this is showing that it has a lone pair electron, and this is actually a pyramidal shape like ammonia. You can see one more example also we can put, not a problem. NH3, this is a well known example of pyramidal structure sp3, and that is PO3 3 minus, that is here. This exactly like ammonia molecules, 3 bond, 3 single bond, and 1 lone pair electrons. This also sp3 and lone pair electrons, that is pyramidal shape, and this also 1, 2, 3, 4, 5, 6, 7. So, 7 electron for chlorine, and it is the molecules shape in such a way that it has a 1 lone pair electron and 3 sigma bond. It is actually shows that it is a pyramidal shape. So that in this case, of course, you can see here S2 minus, P3 minus, Cl minus, all of them having 3 oxygen atoms as a common, so that you can see the number of electrons is 18, 18, 18. So that these molecules, this out of this, these 3 molecules is not only isostructural species, but also isoelectronic as well as isospheres, except ammonia. This also pyramidal shape. So that always isostructural species are the set of molecules or ions having same hybridization and same geometry. That is why it is called isostructural species. Now, let us go for here. Ammonia, of course, isostructural species. If you see the number of electron, entirely different. But even the number of atoms same, but we should not go for isospheres. Isospheres means electron also should be same, but this is xenon is a very heavier atom. Definitely, it will not come under isostructural, isosphere as well as isoelectronic, but we have to check it whether really isostructural species or not. Of course, already NH3 we know that it is 1 by 2, 5 plus 3, that is sp3 hybridization. Xenon, hybridization of xenon trioxide. Xenon being in the inert gas, it has 8 electrons in the outermost shell, and it is a neutral molecule, and oxygen is valence is 2, but we should not get into that spot. Then this is also 4, of course this is also for sp3. And you can see here, this is the ammonia structure, 1 lone pair of electron and 3 bond pair of electron. It is well positioned as a pyramidal shape, sp3. Because of the lone pair electron, it is called sp3. Otherwise, if it doesn't have lone pair electron, it should be concentrated. And xenon having 8 electrons outermost shell, and it has a 3 double bond O. Both are same category, all are isostructural. Okay. So here all of them isostructural species, not a problem, this okay, fine. And now we will see one more examples. CO2, N2O, N3 minus, NO2 plus. Is it all are isostructural or isoelectron species? Let us see here. Already we know that CO2 22 electron, this also 22 electron, this also 22 electron, this also 22 electrons. Nitrogen, this is a 16 plus 7 minus 1, 23 minus 1 is equal to 22 electron. So definitely all of them having same number of atom, same number of electrons. So isostructural, these are all isoelectron species, but we have to check the isostructural or not. Of course, CO2, hybridization CO2 1 by 2, 4. This is a 2 sp hybridization. And you can check here N2O. How do you check the number of hybridization N2O? So we don't have any evidence which one is the central atom. Ultimately, by looking at this N2O molecule, there is no evidence. But in this case, try to write the structure by looking the electron Lewis dot structure, and you will get what type of molecules. Let us say O. Like this, you have to put it. And of course, we know that this is a outermost 6 electron. This is a like this 5 electrons. This also having 5 electron. Like this, it will be there. N2O. Now, I will write the structure in such a way that it is actually obeying the octet rule. So here N okay, maybe I put like this, I don't know correctly, like this. So one positive charge, one negative charge, definitely 2, 4, 6, 8. 2, 4, 6, 8. Actually, this is the actual structure. It has a 2 sigma bond. This is actually sp hybridization. And this one, we came to know that from this structure, nitrogen is a central atom, 5. And the same nitrogen atom having positive charge, that's -1. So 5 minus 1, 4, 4 by 2, 2. That is sp hybridization. This is a correct structure. And is a linear shape. Of course, CO2 also is linear shape. We already know this is a very 2 sigma bond always sp. We know that it is a linear shape. And N2O, and of course NO2 plus also, N double bond O, N double bond O, like this put it. There is one electron went outside, then electron of oxygen atom being the same, it is actually maintained, and it also having the linear structure sp, 180 degree bond angle, that is a linear shape, this also fine, not a problem. And of course, we can verify here also NO2 plus 1 by 2, 5 minus 1, SP, 5 minus 1, this also verified. And of course, what is called another one is N3 minus. N3 minus also like this structure. It has a resonance structure, we can put like this. Of course, it has a 2 sigma bond, definitely this is also SP, linear shape. All of the SP hybridization. Now, last, just one more example, I will show you the isostructural species. This is a xenon difluoride, and another one is a I3 minus. These are all isostructural species. So, xenon hybridization for xenon difluoride HCF2 plus 2, that is a fluorine atom always makes only single bond, it is a monovalent atoms 2, 1 by 2, 8, 10, 5, that is sp3d. If you look at this molecule, this is a one you can able to get 8 electrons. Out of 8 electrons, 2 electrons from the xenon made a single bond, remaining 6 electrons as a 3 lone pair electrons is a planar shape. Actually, this is a planar shape. Like this is actually a linear shape. Linear, but sp3 dehybridization. And one more example I will show you, I3 minus. Generally, potassium iodide plus I2 will under equilibrium, Ki3, it is a titration. Many titration, you have to add a starch, and a titration endpoint you will get the blue color because of the due to formation of iodine molecules. So, K plus I3 form, this one iodine, triiodide ion is existing. If you look at this one, all iodine like this, I make a single bond and it has 7 electron, one more bond, this also having 7 electron, this also having 7 electron, and it has 8 electron now. So, this one, this one, this one. This exactly these molecules I3 minus look like the same as xenon difluoride. It has a 3 lone pair electron as a planar, whereas the remaining bond per electron is in the 180 degrees Celsius. And of course, definitely this also sp3 dehybridization. You can check, not a problem. Okay. So, now students, are you very clear about isoelectronic species, isostructural species as well as isospheres? This is the isostructures very most important. Many competitive exam, entrance exam, they are asking a set of molecules having what of molecules. So that okay. So students, now we will come to know what is isostructural species. Like the same concept, we will go for a different one more another topic in subsequent videos. Please keep on continue watch our Shankar Medico Academy of our videos. So, my name is Dr. D. SUBRAMANIYAN. I am one of the senior chemistry faculty in Shankar Medico Academy. Thank you very much for watching our videos. Thank you.